Okay, so I'm going to very briefly talk about deterministic annealing. For details, you should start with the survey paper by Professor Ken Rose. It's a 1998 survey paper in the Proceedings of the IEEE, and the reference is given in the handout. That's a good place to get all the details. What I have given in the handout is just a practical way to implement it in the specific context of clustering. It has a lot of other applications as well. What's the core idea? The idea is this, that we are talking about, if you look at a clustering problem like k-means, we know that, all we can really do is a greedy approach of alternating optimization, and you go to a local minimum of the cost function. And of course, you can try different random initializations and pick the best, or you can take a smart initialization like k-means plus, and you'll get answers of different levels of goodness relative to the best possible answer. Now, what deterministic annealing tries to do is, it starts from a place where we know that the answer is uncontroversially right, and it slowly makes the problem harder in a way that it's likely that we don't get trapped in bad local minima. So let's start with the soft k-means assignment that we had considered, right? What we have in soft k-means is that we say that pk given xi is equal to pi k e to the minus xi minus mk squared by t divided by all these other terms, summation j pi j e to the minus xi minus mj squared over t. Now we know, we've observed that soft k-means becomes hard k-means as the temperature T goes to 0, so that then you get hard k-means. And we know that that has issues in terms of local minima. What happens in the other extreme? What happens as T goes to infinity? Well, each of these terms goes to 0, and so let me change pen color. These kinds of terms tend to 1, right? So basically, the assignment becomes equal to pi k. You can see all these terms tend to 1, and so you get pi k over summation over pi j, so the assignment becomes pi k. What about that's what happens to assignment. What happens to the update as the temperature goes to infinity? Your mk, what was that? That was summation I p of k given xi over summation I p of k given xi. All of these are now, so this is I equals 1 to capital N, I equals 1 to capital N. All of these things in the denominator are pi sub k, so you have pi sub k times n up there, and you have pi sub k times xi up there, I equals 1 to n. And so what do you get? The pi k's cancel out, and this is the answer you get. So notice that this mk being equal to 1 over n xi does not depend on k. What does that mean? It means that all the clusters, even if you started with different clusters, cluster centers, all cluster centers collapse into one, into the centroid of the entire data set, right? So it's basically, this is completely, the opposite of having a bunch of local minima. We basically just start with as T at high temperatures, where I allow sort of arbitrary amounts of variations around the cluster centers. That's what T large means. I basically just get to the centroid of the data set, and so there are no local minima there. Now, the idea of deterministic annealing is, now I slowly start reducing the temperature and see what happens. So let me try to illustrate with a rough sketch what might happen, right? So suppose I have data that is generated from sort of a Gaussian mixture of three components. Say, I'm just going to make these guys up, right, as I go. So I have one component, two components, and then maybe I put a third component like this. And I've drawn data points from those components marked by crosses. And, I might initially, when I have a very high temperature and run soft k-means, I might get the centroid, which I don't know exactly where it'll sit, but I'm sketching it to be here, right? So now, suppose I lower the temperature and start running soft k-means again. If I look at this, the variation of the data points around this centroid, what should the covariance look like? Well, I haven't computed, I'm just sketching this guy. So let me see. There'll be a lot of variation. There'll be some variation along this direction between these two clusters. And I can see that there is this pull in this direction and in this direction in terms of the variation, and there's a pull in that direction too. So I don't really have an intuition of what the covariance will look like, but let's suppose that the covariance of the data looks kind of like this. Okay, so with a major axis like that. So now if I perturb the if I basically run soft k-means, but I start from the centroid, but I instead of running it with one cluster, let me run it with this and a slightly perturbed version of this. Where I add a random perturbation. The key idea is, and this is like the reason it's called deterministic annealing, is that as I lower the temperature, there are these phase transitions that happen, and when the temperature gets so remember that the temperature is 2 times the variance that we are allowing in the along each dimension. That's sort of what we are expecting along each dimension. And if I look at the standard deviation along this direction, once the temperature that I allow variance that I allow gets smaller than the variance along this axis, then these guys, the phase transition stuff, what it'll do is these guys will move apart. So when I run soft k-means, I generated these two clusters. Before, when the temperature was high, we expect these two to collapse on each other and become the same thing. Once the temperature reaches below a critical threshold, what we expect to happen is that these guys split. And for example, this might move here, and this might move sort of all the way there, or something like that. And I'll basically get 2 clusters. Right, and then once I keep going, I lower the temperature further. Well, this guy has sort of a covariance that might look like this, and that guy has a covariance that looks like that. So the major axis of this is going to be bigger than the major axis of that. Once I lower the temperature below this kind of threshold, then when we perturb this guy, we expect these guys to also split off and go here and here. So what we expect to do as we lower the temperature is to keep getting these splits into these regions, into these. So basically, a small perturbation of a current cluster center, once I get below critical temperature, will cause it to sort of split off into two very different cluster centers, like I've shown here, and formation of new clusters. So the particular algorithm I've suggested, there are many ways of implementing k-means. The particular algorithm I've suggested is, if I'm currently at k legitimately different cluster centers, I basically create 2k of them with these small perturbations once and then basically run soft k-means, and then merge cluster centers that are still closed, that are centers that are close enough. So what might happen is that the 2k guys might collapse back into k, or if you are below the sort of the critical temperature, when a split happens, two of those guys might just go far away from each other and form split off into two clusters. And if the critical temperature is attained in more than one place, you might go from k to k plus 1 or k plus 2 clusters, and slowly, as you keep reducing the temperature, more and more splits happen. I should also note that at each stage, you can stop annealing, stop deterministic annealing, and run k-means. Right? So basically, you started out with one guy, the centroid. You lowered the temperature, and perhaps you got two clusters. And at that point, you could run k-means to conversion and say, okay, now here are my a good solution with two clusters. Then you lower the temperature further, before doing this, running the k-means, basically lower the temperature further, and suppose you get to 4 clusters at some point. At that point, again, if you want to stop at 4 clusters, you can run hard k-means on it and then just stop there. So you can stop at any point of time, or you can have some target temperature or variance at which you are going to say, okay, this is good enough in terms of my the kind of distortion I want to attain, and I'm going to run k-means and stick with that. So this step of running k-means, this means I set the temperature to 0, right? We've seen that soft k-means degenerates to hard k-means, and because it's you're sort of cooling, that's the idea of the lowering the temperature, and at the very end you're basically just making the temperature 0. This procedure is called quenching, right? So you can have, in this process, what you're doing is you're doing this slow reduction in temperature, running soft k-means to convergence at each place, and applying a stopping condition. Your stopping condition could be based on the distortion that you're attaining, the sort of the so for example, you can attain a distortion of 0 if your k is equal to n, the number of data points. You can just set the cluster center equal to the data point. So if you have some target distortion, you can stop there. That's based on that's a temperature based criterion. If you have a target number of clusters, once you get to that target using deterministic annealing, you can quench. So there's a bunch of ways in which you can stop. Now, this is a very, very high level overview of deterministic annealing that hopefully should be enough if you choose to sort of implement it. But there's so much more you can delve into it, and I suggest the 1998 paper by Professor Rose as a very good starting point. So I'll stop here.